Hello everyone, welcome to another chapter in the fuzzing book. Today we're going to look into efficient grammar fuzzing. In detail, we're going to take the grammar-based production algorithm from last chapter, the simple grammar fuzzer, which was string-based, and we're going to replace this by a far more efficient algorithm, which is tree-based. What does that mean? Let me get you back into the ideas of grammar-based fuzzing. So, we are having a grammar which we're using as a producer. So here's a grammar for arithmetic expressions, so to say the standard example for a grammar. And we have seen in the last week how to use this very grammar, because we start with a start symbol and then we take any rule and any alternative in the expansion rule for that symbol. We can keep on replacing expression by any of the alternatives on the right side of the production rule of that symbol. Then we can expand term into factor. We can expand factor into int.int. And we keep on doing so by simple string and replace operations until we have obtained a full-fledged arithmetic expression, which can indeed be very complex. And this is then what we happily feed into our program of choice, which hopefully then fails. So all of this works well, and as we have seen, it's not very difficult to build a string-based fuzzer that does exactly this kind of grammar production. However, this is extremely inefficient, because every time when you want to search and replace something, you have to go through the string. You have this string keeps on expanding and keeps on reducing. This is not very good. And also, which is worse, it does not allow us lots of control over what is actually being produced. So today we're going to look into a different algorithm, namely a tree-based approach. That is, rather than representing the working term in which we keep on expanding symbols as a string, we use a tree instead, and you'll see that this is much, much faster. What does this mean? So let me introduce you to the concept of a derivation tree. So a derivation tree, as the name suggests, represents the set of derivations that we undertake when we are producing a particular string. So I'm going to illustrate this using our grammar, our expression grammar, which we have seen before. So I'm going to make a very, very simple expression here, because things will be easier that way. So a derivation tree starts with a node, and each node in the derivation tree is a symbol. And now we have a start symbol, and this is the first node in our derivation tree. Now, when we are expanding, when we are producing something, we take any of the non-terminal symbols in the derivation tree, and then we add the expansion that we have on the right side of the grammar as a child for that node. So start gets expanded into expression, which means that we can now create a child, namely from start to expression. So now our tree has a first child. And we can continue this again and again. We can, for instance, replace expression by term. Here we have term. And a term becomes a factor. And a factor becomes, say, we're going to make this easy, an integer. And let's say the integer becomes a digit and another integer. And then you can see that if a derivation tree, in the derivation tree, if there are multiple symbols, then they also get expanded into multiple children in the tree. So let's assume we expand the first digit into 4, and the integer becomes another digit. So let's just erase this thing. Okay, no, we're not going to use that one. Oops, sorry. And so we're going to draw another integer here. The integer becomes another digit, and this becomes 2. Oops, yeah, hardly fits. Here we have it. Okay, and now we have a derivation tree in which all of the symbols actually have been expanded, and this derivation tree still contains all the non-terminal symbols that we have used to expand things. How do we get a string out of that tree? Very simple. We traverse the tree left to right, depth first, and then we look into all the non-terminal symbols. Into all the terminal symbols that we find, which in this case happens to be 4 and 2. So this whole tree corresponds to the string 42. Here we go. So the advantage of this, doing this in a derivation tree is that every step in derivation simply means adding another element to the tree, namely adding the symbols on the right side of a derivation rule, which of course is far cheaper than taking a string and doing a full-fledged replacement. The one step that is slightly more expensive is at the very end when we want to extract the string, because then we have to traverse the tree, but this is very negligible. Furthermore, such a derivation tree offers us more control over what should be expanded and when, because at any point we can inspect the derivation tree for things that we already have done. For instance, we can find out that we already have an expansion from a factor into an int, and we have an expansion from an int to a digit. These will be useful when looking at grammar coverage in the next chapter. So let's get back to our actually notebooks. So we go back, and here we have the chapter on efficient grammar fuzzing, and everything that I have just demonstrated by drawing is actually something that we also have here as full-fledged visualizations in here. So let me just quickly get to the most important point here. This is the point on derivation trees, and we have a short explanation on how derivation trees come to be. And the neat thing is you can actually visualize all these derivation trees by yourself. We have an internal representation, which is a pair of symbol name, and then comes a list of individual children, which is a not too unusual representation for derivation trees as tuples. And we do have a function that actually allows us to visualize these at all times. So we can take a derivation tree, feed this into display tree function, and then you can visualize a derivation tree at any point right within the notebook. This also allows us to actually visualize the progress as it comes to grammar fuzzing. So we can look into what it means to expand an individual node, and expanding an individual node is something that we can see here. We start with a start symbol, and then we pick an alternative to be expanded, and we keep on expanding this again and again. Here comes the function expand node randomly, which does precisely that. And now we see that we have an integer, and the integer becomes a digit, and the digit can then of course become another digit. How do we have that? Here comes the digit. Digit becomes 8. So these are all expansion functions that are part of our fuzzer. Our fuzzer is a full-fledged class named grammar fuzzer, and it's pretty sophisticated, not only in the sense that it works on derivation trees and keeps on expanding them ad infinitum actually. So we can get very complex trees in here. Something like that, for instance. This is expression plus term, factor, and with every step our fuzzer looks into non-terminals that are not expanded yet, that is, non-terminals that have no children, and it keeps on expanding the tree and again and again. Now the interesting question is, how do we control this expansion? And for this we adapt a number of interesting algorithms. So in essence we have 3 phases. The first phase is we keep on expanding until a minimum length is reached. So we can actually control that we want a minimum length of the input. So we keep on expanding, and we also choose the alternatives that lead us there, which is very interesting. Then we have a stagnation phase in which we just keep on expanding, and then we keep on doing this until we have reached a maximum number of non-terminals. And once we are there, then our algorithm is set such that it always picks the expansion that actually closes things, that is, in which we have the smallest number of future expansions. So first we inflate, then we stagnate, and then we close things such that we actually always get to the point. This makes the algorithm also very robust, meaning that in contrast to our simple grammar fuzzer, there is no risk of the algorithm running into an endless loop or failing to expand. All of this is well done in here. I welcome you to experiment with Grammar Fuzzer yourself and to try this out. Again, we have the Jupyter Notebook, and we have a log parameter for the Grammar Fuzzer, which you can set to true, and then you can see all the individual steps. And I welcome you to toy a bit around with the algorithm. The Grammar Fuzzer class also is the base of future fuzzers that we're going to look into. And these future fuzzers hook into the algorithm by overloading specific methods. In particular, the choice of individual children to be expanded. This is the core method, which defines the strategy, which child are we going to expand. And this method is what we're going to overload in other even more sophisticated strategies. So have a look into Grammar Fuzzer, and don't forget to try this out yourself with your own experiments in the Jupyter Notebook. Enjoy!